for today. Before introducing our speaker, let me remind you of the events in the coming days. As I guess some of you know, just judging by what I don't know here, there's a conference this weekend on space-time functionalism starting tomorrow at 9. Is that correct?
Breakfast at 9.
Breakfast at 9. So there will be breakfast, bagel, and various delicacies. If you're not tired of your bagel, you have more tomorrow morning. But we have a few other things. So join us for breakfast at 9, and it goes on Saturday and Sunday. It should be quite a wonderful event. On Tuesday, we have a lunchtime talk by Matthias Michel, who is at NYU right now, and is going to be talking about validity drifts in psychiatric research. You're all invited for this talk. Matthias is coming on Monday afternoon, I believe, and will stay part of Tuesday. If you want to talk to him, he works a lot on consciousness, independently of his work on validity drifts. If you're interested in consciousness, he does really very impressive work. I'm sure he'd be delighted to talk to you. So let me know. And on Friday, David Gouveia, who was a visiting fellow, she's right there, last semester, and a visiting scholar this semester, spent the whole year with us, is going to be talking about crafting scientific narratives. Today, we are delighted for the second time this year to listen to Adam Koberinski, who was and still is for a few more weeks our postdoctoral fellow. We were just talking about that a minute ago. Here at the center, we've been very lucky to have Adam with us. It's been a wonderful year. He worked on the history, methodology, and foundations of quantum field theory, as well as cosmology. He got his PhD from the University of Western Ontario. He's got more than one connection with Pete, because not only did he spend the year with us, he also was a postdoc before that with Doreen Fraser, who is a former Pete PhD. So he's got a deep connection with us. He's published very widely on all possible topics. Physics. All possible topics. But in really all the best journals in the field, philosophy of science studies, and so on and so forth. And today, Adam is going to be talking about renormalization group explanation, but the floor is yours.
Thanks, Edward. So I knew going into making this talk that I was going to have a mix of a bunch of people who do philosophy of physics that are both at Pitt and here for the conference, and then people in Pitt that maybe aren't philosophers of physics. So I tried to balance some topics a little bit to cover some background on that should hopefully be interesting, at least the first half. If for those of you who aren't that into physics, you could probably tune out during the second half, and I'll tell you to wake back up for the conclusion, so you'll get that. So I jumped on the train since for people who have been around all semester. We've been talking a lot about AI art, whether it's general intelligence, things like that. So I jumped on the bandwagon of getting my cover image by using a DALL-E prompt. It actually took a really long time. I found out I'm either quite bad at using DALL-E, or it's really bad at understanding what renormalization group flow is. And this was the best it could do. That kind of looked artistic. If you squint hard, it kind of looks like, I don't know, trajectories in theory space. Yeah, it could be two shrimp. It could be renormalized. I mean, maybe just a, AI art isn't going to take over at least all domains anytime soon. But yeah, it was colorful and pretty, so I thought I'd at least put it out. Okay, so I'm going to start with a bit of an introduction on what the renormalization group is, in a sort of qualitative way first, by playing some fun analytic philosophy games about meanings of words. So that may be the interesting part if you're not a philosopher of physics. Then sections 2 and 3 will be kind of still at a more qualitative level, kind of going over how renormalization group methods are used in statistical mechanics, a sort of classical form, and then in quantum field theory. Then I'm going to quickly talk a little bit about renormalization group explanations of universality, which has been a big focus in philosophy of physics. Bob especially has done a lot of work on this. I'm mostly going to cover a little bit of Bob's view. If I get it wrong, it's more just a contrast with what's coming later. So you can pick on me after. But the idea is that in particle physics, we get these sort of different types of explanations that are interesting. We don't really have a good analog for universality. And then, yeah, some conclusions. So not getting away from AI art, this is one of the reasons I went to AI art. You know, figures often make things nice and clear. If you're reading a physics paper and you don't really understand the equations, sometimes the figures really help. This is from one of the original papers on developing renormalization group methods. I mean, I don't really understand what's going on here without referring back to the paper. It's not very clear at all. So I'm going to just kind of quickly go over a little bit of terminology and point to some work that I've done a little bit of and some other people are working on, looking at the sort of history and methodology of the development of renormalization group methods as well. So very broadly, renormalization group is a collection of formal tools used to study the behavior of theories at different scales. It's understanding scaling behavior of particular types of theories. Typically, that's talking about distance or energy scales, which in physics in the right units are kind of inverses of one another. So you can talk about what behavior at large distances, behavior at low energies, and kind of use those interchangeably. It was kind of first developed. I mean, there's a rich history here that I want to gesture to a bit, but it was kind of first developed in particle physics, taken over to statistical physics and condensed matter physics, and then kind of brought back into particle physics. James Fraser has an interesting paper on this, looking at the origins. That's the paper referenced here. Doreen also has a paper on this. And so I haven't actually seen things coming out, but there's a sort of working group that's kind of working on some of these ideas that involves a kind of group of physicists around that I'll gesture to a bit later. It's a really sort of interesting topic about how these things come out if you're interested in history and philosophy of physics. So I just kind of want to gesture to that, but that's not really the point here. One really important thing is that the renormalization group plays an essential role in understanding and justifying effective field theories, the effective field theory worldview sort of in quantum field theory. And also, as many of you who probably don't engage as much with philosophy of physics literature are aware, also really important for explaining universality phenomena in bulk systems. So like things like phase transitions having the same sort of critical exponents in very different types of systems. So that's what Bob's worked on. I picked one paper. Yeah, I could have filled this slide with references to his work on this. On the side of particle physics, I'm also going to lean pretty heavily on a paper I wrote with Doreen that was just published. So I'm just putting that there as well. So here's the sort of old school analytic philosophy. You know, you think, okay, that gives me a little overview, but like, what about the name, the renormalization group? Is this, I should, you know, if it's a good name, I should learn something about what it is by thinking about, you know, the renormalization group. What does that describe? And so it's maybe for many of you not quite clear as to what that means. And I think that's probably a good point. It's actually a kind of poor name on many fronts. So I'm just going to quickly go over why it's a poor name to kind of help explain a little bit more of what the renormalization group actually is. So first, is it really a group? In mathematics, what we mean by a group is, I mean, there's different ways of formulating it, but here's a non-empty set G in some combination operation that I've given star that obeys the following properties: associativity. So for all elements in G, you can combine, if you combine these two first and then this one, it's the same as combining these two first and then this one. There's an identity element, there's a unique element of the set, such that for all other elements of the set, the action of that element on it just gives the same element back. It's kind of like doing nothing, the identity element, and that also the group has an inverse. So for all elements within the group, there's a unique element that's its inverse, such that if you combine from either side, you get the identity map. So you think, physicists are pretty well-versed in what a group is. So if anything's right about this, that, the renormalization group, it must be a group, right? The answer is not always. You'll hear, I think it depends on the formalism. Often certain types of transformations are better interpreted as a semi-group, something that does not have it's not reversible. So you kind of, if you've heard a little bit about renormalization group stuff of like coarse graining or throwing away degrees of freedom, that's the sort of thing we're talking about. It's a sort of semi-group transformation. So once you've thrown them away, you can't recover them in some sense. But there's also forms that are a full group. So that's again this sort of loose collection. There's different sort of forms of the renormalization group, and some of them are actual groups, but it's kind of a boring group. Sort of a one parameter group of transformations. It's just changing scale up and down. It's reversible, but even as a group, it's a pretty boring group. So the name group is not maybe ideal. It's sometimes accurate, but it's kind of either wrong or kind of trivially true in some sense. So okay, it's maybe not a group, but it's got to be about renormalization, right? That's the renormalization group. If it's not a group, one of these words has to be right. And again, the answer is kind of sometimes yes. Sort of has historical origins, again, in particle physics, about understanding how renormalized terms in a quantum field theory change under sort of redefinition of parameters. It's also used still today in some forms as a conceptual justification for how renormalization works, why we renormalize theories in quantum field theory. But it also has much broader applications that don't really touch on renormalization per se. So again, kind of yes, sometimes. I think this is probably the renormalization is the best word of the three. It is about renormalization. It has historical roots there. It kind of makes sense what you call it that, but that's also kind of a narrow focus. And sort of underlying all this yes, no, maybe sometimes is that the is a bad word to describe the renormalization group. There isn't some sort of single unified formalism that is just the renormalization group. It kind of takes different forms depending on what sort of problems you're considering, depending on the theoretical framework you're using. So it's actually quite hard to just be given a problem and to build a renormalization group for that problem. Because there isn't this sort of background unified formalism. So that's kind of underlying all the sort of ambiguities here. So if you were already confused about what the renormalization group is, I hope I've confused you a little bit more, but also in a way that kind of gives you a little bit more background. It's not, kind of, you can say the, and then renormalization, and then group. Kind of at a broad stroke, just think of them as sort of scaling transformations on the theory. Cool. So we're going to look at the sort of cases that are discussed most in the philosophical literature, and ones that are kind of easiest to visualize. Renormalization group transformations in statistical physics. These are actually quite powerful. It's not like this is a really special case that only has application in like toy models or something. It's actually quite useful. It's just also simpler to think about. So to start, we can think of having a particular toy model that we're going to study, the Ising model. What this is sort of a lattice of degrees of freedom, each of which is sort of a binary degree of freedom. You can think of it as often kind of given a concrete interpretation as at each point there's a spin degree of freedom. It's either spin up or spin down. That's what all these arrows are. Sort of this is sort of a square lattice, but you can do this in different shapes, in different dimensions, whatever. Typically, sort of for simplest interactions, we write down a Hamiltonian describing that system. The Hamiltonian describes the energy of the system, and it encodes different interactions between the degrees of freedom. The simplest one is just a sort of nearest neighbor degree of interaction, so that each spin only kind of knows about the spins around it, and there's some sort of correlational structure between those. What we find in a sort of, if we just look at the Ising model by itself, when we use a Hamiltonian like that, there's sort of a critical temperature, at least in 2 dimensions or more. There's a critical temperature where, if you imagine this as being like a magnet, like a simple model of a magnet or something, as you lower the temperature, these spins, they get less sort of random motion from just sort of the background temperature, and they start to align with one another. And there's a sort of critical point at which they all align, and the correlations, you can describe this as a sort of divergence of the correlation length between each spin. So, as that diverges, what that means is that, every spin is correlated with every other spin. They all kind of align, you get magnetization. So that's like one kind of small model, but it's a good one to use the renormalization group on because it's relatively straightforward. So one sort of renormalization group transformation due, I think, originally to Kadanoff is a sort of block scaling transformation. There's many ways you can do this. This is just one example. You take a bunch of the spins on the lattice. So here we've given a length scale for the separation. It's just some constant. you group all these spins together into clusters. And then so here the rule for how you sort of transform the theory is just a majority rule. If more of the spins in that cluster are up, then you reduce them all to one spin up. If more of them are down, you reduce it to one spin down. And so if you kind of like, if you have a big enough lattice and you zoom out, it kind of looks the same as the original theory, except you've thrown out a bunch of degrees of freedom. You now have a bigger lattice spacing. If you rescale that lattice spacing to kind of make it look even more the same as the original theory, that's sort of whole process as a form of renormalization group transformation. So this is clearly a form of coarse graining, at least in this sort of majority rule form. You don't know what, so you go from 9 degrees of freedom to 1 in this example. You don't know what those other 8 degrees of freedom were. You just know that more of them are, you lose a lot of information when you go over there. But it's a sort of way to rescale the theory. You can think of what this theory looks like at a different scale, and that gives you a form of renormalization group transformation. And this becomes quite powerful as you kind of near a critical point, like where there's a phase transition to spontaneous magnetization or something like that. Because you can kind of, when you make this transformation, like in the form of the equations, the Hamiltonian is going to look a little bit different. Obviously, you've thrown out a bunch of degrees of freedom. The nearest neighbor interactions are now changed. You have to kind of massage the form a little bit. But yeah, as you near the critical temperature and sort of have an infinite idealization as well, you'll find that sort of transformation reaches a fixed point. You can keep block scaling because, again, if all this, you can think about it specifically at the critical temperature when all the spins kind of align. If your majority rule is going to keep giving you the same thing, right? Like if all the spins are up, you can kind of throw away degrees of freedom, rescale, and get a new theory that looks the same where all the spins are up again. So the renormalization group kind of reaches a fixed point, and that's actually quite powerful, sort of for understanding, to sort of give a general class of how phase transitions, not just in magnetization, kind of work. And one way of thinking about that as you near criticality is that whatever small scale details were relevant to the dynamics, I mean, this is quite a simple model, so you know what those details are, but even in cases where you don't, whatever those small scale details are kind of get suppressed near criticality. In the sort of technical parlance, we talk about terms in the Hamiltonian that are relevant, irrelevant, or marginal. I've put infrared relevant and infrared irrelevant because long distances correspond to like low energies. So the infrared means kind of low energy. So what you'll find is that there's only certain parameters that actually matter. In the infrared, there's only a few small number of relevant parameters. Many are irrelevant. You might have some marginal depending on the specific system. Cool. So it's easy to see that as a sort of, like I said, coarse graining operation. It's irreversible. And it actually turns out that there are many systems that kind of fall into the universality class of the Ising model in the right number of dimensions. So you can model it all within, like, you can use that model to kind of get the same physics out at a critical point for three-dimensional magnetization, for superfluidity, for some materials as they're kind of boiling, that sort of phase transition. So it turns out to be quite powerful. You get a bunch of different systems that are all kind of described in the same sort of way because all of their little details get kind of washed out and only sort of bulk features start to matter. And yeah, so the nice thing about the sort of coarse graining interpretation or this coarse graining approach is it's really clear you're just throwing out the microscopic details. You're not like suppressing them really heavily, but still kind of keeping track somewhere. So you're literally just throwing them out. And so you can really see how in the sort of idealized case, all these different systems will actually converge to the same sort of physics near phase transition. And yeah, the renormalization group is sort of the formal tool that shows you in a sort of technical sense how those terms are relevant to the behavior. So there's also renormalization group methods that get used in quantum field theory. And here I'm using David's way of talking about quantum field theory that I do mean condensed matter physics as well. Just because the formal tools are the same here. It's not a class, so that was kind of classical setup, which is useful for modeling some systems, but in some cases you do need the fully quantum treatment, in which case the sort of formal apparatus is quite similar. So at this level of discussion, there's no need to distinguish. And so this picture is just, if you don't know what a quantum field is, this is kind of a way to visualize it. It's like a mattress if you're Anthony Z, it's a mattress at least. It's about as good of a pictorial representation as you can kind of get of what a quantum field is. So
Is it quantized?
yeah, to be fair, yes, it's a quantized matrix, but as a rough and ready approximation, look, it's kind of looks like that, a bunch of little springs connected one another at once in space. So there's sort of two forms of the renormalization group, which kind of get you to the same point for most practical applications, but are slightly different. And I think I'm just going to distinguish them just because. So there's sort of the Wilsonian form of the renormalization group, which is kind of the one that's more commonly studied. This is due to Ken Wilson mostly, but it finds its sort of historical fleshing out in that paper with Kogut in 1974. Again, historically was actually based on constructing an analogy with the Ising model. You kind of transform the Ising model, turn it into something that looks like a field theory, and then you can kind of map the transformations over, because again, constructing renormalization group transformations from scratch is really hard. So if you have a domain where it already works, then you can try to figure out how to massage that into the form of something that of a new domain, then you usually do that. Yeah, so that Doreen has a paper that I've already talked about on this. I have a paper that touches a little bit on the development of the renormalization group as well. It's the power of the Wilsonian sort of approach is that it regularizes and renormalizes theory all at once. So you kind of start with like a bare theory, or you can start with a bare theory and then use this apparatus to sort of make an overall well-defined theory right from the start. So this is sort of a formal. Yeah, so it works at the level of sort of a generating functional, which is the path integral sort of thing, which is essential to modern formulations of quantum field theory. You start, actually, I think I have it on the next slide. So you start with some sort of bare theory. What you have here, this is the action. This is kind of like the analog of the Hamiltonian. It describes the dynamics in some sense. It's exponential. You're integrating over field configurations. That's why it's called a path integral. You're integrating over all the paths that the particles can take, or the fields configurations can take. And the transformation starts by picking a cutoff, which is capital lambda here, and kind of splitting the field into low momentum modes and high momentum modes, those with momentum less than lambda, those with momentum greater than lambda, so the H and the L superscript are high and low. And what you want to do is kind of forget about those high energy modes. Those are too, they're hopefully not relevant to our physics. Let's just try to integrate those out right at this sort of formal level. So you split up your action in terms of those fields, you integrate them out. So you actually carry out this integral explicitly when you can. And what you get is a new path integral that's only the low energy fields, but also now has dependence on the cutoff. You try to massage the action so it looks as much like this one as possible. There may be new terms that come up that you kind of need to put in because you've integrated out some of the physics, right? So you might have new interaction terms amongst the low energy fields. So that's the Wilsonian form of the renormalization group. You kind of iterate that process. You go with a slightly lower lambda, like lambda prime. If you keep doing that, you can kind of get a sort of differential form of this, which is the renormalization group transformation. At this level of description, it kind of sounds like this is also a semi-group sort of thing, right? You're integrating out high energy degrees of freedom. You can't really recover those in some sense. In some sense, that's kind of right. At the level of the fields, you're throwing away information. But there's some caveat there, because what you really want at the end, so what comes out of this sort of approach is an effective field theory view. You get a theory. The most general form, so the Lagrangian is something that is in the action, that L, you can think of it as the S is like an integral over space-time of the L. In general, the most general form of your Lagrangian will be have all these interaction terms that are compatible with the symmetries in the fields that you've chosen for your theory. So technically that's an infinite number. And so when you do this renormalization group transformation, the easiest way to keep things in the same form is to keep all of those, or keep track of all of those terms. I got disconnected. Sorry. Disconnected from Zoom? It disconnected and then reconnected. Okay. I don't know. So. Yeah, I'm not. So this is still working. So I apologize.
Can you see your screen?
I have to stop share. I can still. Oh no, I can't. Okay, so I can see mine. It's not on there anymore.
Keep going.
Yeah, I'll keep going. Where was I? Oh, yeah. So you have this sort of new form. This is sort of the effective field theory form of the Lagrangian that just includes all the terms. You can kind of parameterize that theory by like an ordered set of the coupling constants if you order them in terms of like increasing mass dimension or something like that. And that gives you a big theory space. And it turns out that the action of the renormalization group on that theory space parameterized by these couplings is this beta function, which is a change in the coupling constant with the logarithm of energy. And that's a fully reversible transformation. So once you're at the level of this sort of theory space, you've kind of done there's some sort of sleight of hand going on here. We can talk about that more a little bit, that you've gone from a semi-group transformation at one level, and now you've got a group transformation for the things that you maybe care about here. Cool. And you get the same sort of setup as before, except so in 4-dimensional space-time, there's sort of a principled way of separating out operators. That terms with mass dimension greater than 4 will be infrared irrelevant in the same way that we had irrelevant terms in the classical case. I mean, there's technical differences, but you get the same basic idea. Terms with mass dimension less than 4 will be relevant. Those things grow in importance at low energies. And then terms with mass dimension that are right at 4 will be marginal and will stay the same at different energies. Those are typically, if you're looking at older approaches to quantum field theory, those are the renormalizable terms. Those are the things that people were really after in the development of the standard model. So I've already kind of said this. There's is this a reversible transformation? Is this coarse graining? At one sense, kind of yes, in one sense, kind of no. The beta functions, which at one are reversible, so in that sense, it's a reversible transformation. But if you look at the level, kind of at the abstract level that I was talking about before, and looking at the setup of the path integral, there is some sort of irreversibility to that. So not that that's super important for this right now, but that's something to keep in mind. So there's a sort of equivalent, I mean, not quite equivalent, but like a similar formulation to the renormalization group, which actually came about earlier due to Gelman and Lowe in 1954. It's kind of, you get the same basic idea, but what they do is they start with an already renormalized theory, or a theory that's already well defined. Like if you're looking, you can generalize past renormalizability and have an effective field theory where you fixed the couplings already. So you're not starting with a bare theory like you are in the Wilson approach. And so the only thing, you'll notice the equation is the same. The only thing I changed the lambda to a mu. It's really doesn't actually mean anything. It's just more to keep in mind that this is like renormalized parameters renormalized to some actual reference energy mu rather than some high energy cutoff scale. You can, I mean, it doesn't actually, the symbol doesn't matter, but it's just helpful maybe to keep those apart. So you get this beta function by requiring the invariance of the endpoint functions with change in that reference energy scale. Zoom popping up on my screen again. Okay. And so yeah, this is all like this from the start is a reversible transformation. There's no ambiguity, but you get the same sorts of beta functions. So in some sense, these are equivalent once you've kind of set up a theory space in which to do your renormalization group analysis. So yeah, typically this is kind of used more in practice because we often already start with theories and want to know how theories that we're already using at some energy scale are like how those couplings might change at different energy scales. It's also more tractable than the in-principle approach of keeping track of an infinite number of coupling constants. We can never actually do that. So you might start with just a purely renormalizable part of a theory and see how those couplings, if you treat that theory as completely well defined by itself, you want to see how do those coupling constants change with changes of energy scale. And you can get good behavior, you can get bad behavior. So quantum electrodynamics and like sort of toy 5-4 theory have bad behavior. As you go to higher and higher energies, there's a point at finite energy, not as energy goes to infinity, but at some finite value where at least one of the coupling constants goes to infinity, which tells you that sort of theory kind of loses meaning, it kind of blows up. Fortunately, those are like really high energies that were, you know, I think for QED, it's like 10 to the 200 and something like electron volts. So these are like hundreds of orders of magnitude higher than what we think, you know, the Planck energy is, or things like that. So in practice, it's not something to worry about, but it gives you sort of a way to study the sort of behavior. If you wanted to think, is QED a sort of theory that could make sense at all energy scales, at least in the way we have it now, the answer is no. It has this sort of what's called a Landau pole. You can have sort of well-behaved versions as well. So in the UV for QCD, quantum chromodynamics describes a strong interaction. You get what's called asymptotic freedom. As energy increases, the strength of the coupling constant goes to 0, and you actually have what's basically a free theory of quarks and gluons. And then the converse of that for QCD is at low energies, the coupling strength really increases, and you get this sort of idea of confinement where we don't see free quarks at low energies because they're bound together into hadrons, pions, and things like that. Cool. So again, reversibility course grading is it's reversible. There's no course grading. We can kind of go past that. So now I'm going to do a little bit of Bob exegesis. I'm mostly just taking a couple quotes. So hopefully I haven't done too bad a job. But again, this is the function that serves as mostly to contrast with the case in particle physics. So we have this sort of, to kind of recap where we are at the moment, we have this wide ranging, highly applicable formalism that can be used in all these different cases. There's a lot of similarities in the formalism in how it's used in sort of relativistic quantum field theory particle physics and how it's used in condensed matter physics. And so that might license you to think, okay, there's going to be a lot of ways that we can kind of see how things work in one case and then kind of carry over our understanding or interpretation from the other. In a lot of ways, that's right. My point is just kind of being careful about which things you're carrying over. This is kind of a relatively, I would say, maybe not trivial example, but an example that I think should be non-controversial for at least some ways where we think that sort of easy transfer just doesn't work. So we have renormalization group explanations of universality. What is universality? I mean, again, like there's many papers I could have cited. This was the one I was reading a couple of weeks ago. So I picked this 2019 paper where Bob says this is kind of meant for a more general audience, at least at the start. So this is sort of a first pass kind of way of thinking about it. Universality refers to the existence of patterns of behavior by physical systems that recur and repeat, despite the fact that in some sense the situations in which these patterns occur and repeat are different. So something kind of like a multiple realizability. We have a bunch of different systems that we think are different, but yet in some sense they display the same types of behavior in certain regimes. And that's, you know, we see these systems out in the world and we want to sort of explanation for how this works. So one example is the universality of critical phenomena. So this is one where the renormalization group comes in quite a bit. So things like phase transitions, as I was talking about before, boiling liquids, ferromagnetism, superfluidity, superconductivity. There's all these different types of phase transitions, different systems that exhibit them. And nevertheless, they kind of fall into universality classes of a bunch of different systems all kind of display the same types of behavior in certain limits. So that's kind of what comes out. So this is sort of, just to be clear, that this is a generalization of phenomenon observed empirically. Like, it's not something you just kind of go out with your eyes and see, but we studied these systems and we see that they have certain properties that look the same. And sort of, you have this empirical phenomena that cry out for explanation. In a lot of these cases, we at least kind of have some sense on the microdynamics, at least enough to know that the microdynamics are quite different. We might not have a fully worked out exact theory of, you know, the microdynamics of the fluid or something like that, but we have some idea of how to handle them. And we know that in certain regimes, these systems are quite different, but nevertheless, they display the same sorts of behavior. So yeah, again, it's an empirical phenomena or sets of empirical phenomena that require explanation. And so two of the things that are important to explain when you're trying to explain universality, which is where you invoke the renormalization group, are these stability properties. So these features, why are phase transitions stable under the perturbation of microscopic details of the systems? And why are the universality classes dependent upon the symmetry of the order parameter and dimensionality of the system? So you need to explain the stability under perturbations to some parameters and why they seem to be sensitive to the dependence of other parameters. And this is where we use the renormalization group. So again, this idea of relevance and irrelevance comes into play here in a sort of technical sense. As you approach a critical point, a critical temperature usually, systems start to get longer and longer correlations between their micro details, and so the renormalization group transformations, as you kind of keep rescaling and flowing outwards, what you find is that many of the micro details are irrelevant in the sort of technical sense. So that explains part one. All of the features that seem to be irrelevant in the non-technical sense seem to be irrelevant to the description of critical phenomena. It's because they're irrelevant in the technical sense. So I mean, it's kind of, that's one place where the language being used is actually quite appropriate. So yeah, and then the explanation of the other is that the parameters that do seem to matter are things that are either marginal or relevant. Things that either grow in importance as you kind of zoom out further and further, or things that at least stay equally important. You can't kind of suppress them away under renormalization group transformations. And so these sorts of universality type explanations can employ, depending on the systems and depending on how much detail you want, can employ both the classical statistical mechanical models in simple cases, but also can use the quantum field theory methods if you're starting with a much richer sort of micro description. Okay, so that's a brief summary of universality and kind of where it comes from, why it's worth explaining, why it's sort of an interesting philosophical topic. And then here I'm going to talk about why it's not something we talk about in particle physics. Okay, so let's start with thinking about what the standard model is. The standard model of particle physics, constructed in the 1970s, is our kind of best theory of matter and the forces between matter. 3 of the 4 kind of physicists use the term fundamental forces. I mean, that's kind of slightly a misnomer, but the most fundamental forces we know of describes, we use the standard model to describe all of those except for gravity. So the strong nuclear force, the weak nuclear force, and the electromagnetic force. What this theory does is it's sort of in some sense, a kind of universal theory. So you're describing physics of like the strong force, like all systems that experience a strong force are described by the same sort of Lagrangian or interactions. So that's just a contrast with the cases in statistical physics where you don't have, like you have different systems that you might use the same theoretical framework for, but you come up with slightly different theories for. So you have different microphysics. Here it's kind of all of the sort of elementary particles that we know about kind of share in the same sets of forces and interactions. So it's a sort of unified description. So I put on the left here the set of things that I talked about for universality, and then on the right, kind of the contrast in particle physics. This is a clear case where we don't really have something like universality to explain, at least not in the same sorts of ways that it comes up elsewhere. So as I said before, we think of universality as sort of a generalization of, or some generalization of phenomena that are observed empirically, that we have a bunch of distinct systems that all, in fact, are observed to display the same behavior near a critical point, or near their critical points. We don't really have that in particle physics. We don't have a bunch of different systems. I mean, in some sense, we have a bunch of different systems that are all described by like QED or something, but that's not really universality, because we think they're described by the same microphysics. And I mean, I'm sure there are people out there who have ideas that maybe at the fundamental level, there's actually a bunch of different physical, like beyond standard model physics is actually different in different regions, but it all arises to the same. But that's barring that sort of speculation that I think would be considered implausible by most. We don't have the same sort of thing in particle physics. Everything is kind of described by the same microphysics, and we expect that even future theories, those things will be described by the same microphysics. So one other thing that's sort of kind of an epistemic thing is that we don't know what that microphysics is. So underlying the standard model, like I said, there's a possibility that we could have something where there's distinct beyond standard model physics in different regimes of the universe. I guess it's conceptually possible. I don't even know how we'd have that, how you'd be able to prove that or figure that out, but it's at least very unlikely, but I'm going to leave that as a sort of epistemic possibility. And so the stability arguments that you get, like the analogs of the stability arguments for universal phenomena, are kind of counterfactual stability arguments. Like if the high energy physics, whatever it is, could have been different, it still wouldn't have mattered to what we actually see at the LHC or something like that. So in some sense, I mean, I don't want to get into too much of a fight over exactly what counts as universality, but at least in the distinguishing features here, there's sort of no phenomenon of universality to be explained. If you want to use universality in a wider sense, I'm fine with that, but there still are these sort of differences. So what do we use the renormalization group to explain in particle physics then? If we don't have, the sort of big focus of study, again, if for those of you who aren't in philosophy of physics, you hear renormalization group stuff, you're probably thinking of universality or something along those lines, or critical phenomena. If that's sort of not what we're in the business of doing in particle physics, then why are we using renormalization group stuff at all? We get sort of more local, I mean, there's still a wide range of purposes, and that's kind of, I'm just going to gesture towards some stuff that I've worked on with Doreen here. There's a wide range. You can think about local explanations of stability of particular theories, counterfactual variation in theory space. So yeah, there's a bunch of stuff. Of the three I'm going to focus on are, one is sort of a historical thing you might worry about, of if you know a little bit about the history of particle physics. The standard model was constructed basically by imposing a requirement of renormalizability on theory construction. And then it turns out, we get the renormalization group, we figured out how that relates to renormalizability, and it turns out that renormalizability is not really that important, at least for our modern perspective. We don't really care. Write down whatever theory you want. It can be non-renormalizable. We have ways to handle that. So you might wonder, well, like, why was that such a good guide for theory construction? Constructing the standard model, which, as far as we know now, is still the most empirically successful precise predictions that we've ever had, and continues to boast those. I mean, there's starting to maybe be a few cracks here and there, but they seem to come up and then get resolved with future measurements. We'll talk about that in the Q&A. That's not as important. But you might wonder, why is that? If renormalizability is not that important, why has this theory that was built based on it kind of withstood the test of time and continued to be successful? You might also wonder, sort of, this is what I think of as kind of the analog to a universality style argument, the sort of epistemic stability of low energy physics from details of unknown high energy physics. So that's kind of informed the closest analog to the universality arguments. And then you might wonder, again, I kind of gestured towards this when I was just talking about one, the continued success of the standard model without including, if it's actually an effective field theory that has all these non-renormalizable terms, why haven't we picked any of them out yet? Why haven't we found them? So I'll just kind of quickly go into these. So the phrasing of these explananda are just from the paper with Doreen. It doesn't, I've kind of explained them already, so it's not a huge, the wording isn't that important. So why was renormalizability successful? Well, the renormalization group can also explain this. Suppose we were to start with the standard model as an effective field theory, including all of those infinite terms, many of which are non-renormalizable. We put in some cutoff scale, the sort of upper, like a bound where we think the theory is going to break down. It could be the Planck scale, it could be lower, as long as it's kind of, significantly higher than energies we've already confirmed it to. But if we kind of use the Wilson approach and kind of start with the theory up by that cutoff scale and flow down under the renormalization group to energy scales, what are called epsilon here, that are significantly less than that cutoff, the original cutoff, then all these non-renormalizable terms turn out to be infrared irrelevant. They get heavily suppressed by, the more non-renormalizable they are, the more they're suppressed by more and more powers of the cutoff. So you get terms like epsilon over lambda, which are, go to zero. So you could say, well, even if they had the sort of modern understanding now, this would have been a good heuristic for dealing with at least a low energy approximation to whatever higher energy physics, because as long as you are in a regime where the energies you're considering are much lower than where you expect the theory to kind of break down, just focusing on the small number of renormalizable terms will be a good approximation to the actual physics, since all the other terms are kind of negligible. So that's, I mean, the renormalization group justifies that sort of successive renormalizability in some sense. So again, the stability of low energy physics, low energy effective field theories seem to make predictions. Well, they do make predictions that are empirically robust with respect to some set of possible variations in the high energy successor. So you can think of this as the analog to the universality, like a bunch of different systems with distinct microphysics all flow down to the same sort of critical behavior. Our effective field theory is like the analog of the critical behavior, and then we're trying to go back up and be like, well, what's the theory that this is an effective theory too? And what seems like a really cool phenomena when you invert it is kind of pessimistic in some sense. It turns out you can't really find out much about high energy physics from its low energy effective field theory, because when you invert that flow, I have a diagram coming up later. I'll just leave it for now. So you've got this theory here, but when you invert the flow up to higher energies, you keep widening the scope of possibilities that are compatible with that. So this you kind of invert that sort of universality type explanation. You get this sort of counterfactual robustness or counterfactual stability that, had the high energy physics been, with these couplings, or had it been with these couplings in this space, it wouldn't matter because they'd all flow down to the same sort of effective field theory at lower energies. Yeah, so again, we use the renormalization group, that sort of theory space and flows and irrelevance and relevance to provide that explanation. There's something like this sort of claim that's used to ground a form of it's called effective realism. It's like a forward-looking realism that we should be confident in certain features of the physics of the standard model, because we know under renormalization group flow that they'll be stable under whatever, regardless of what the future physics kind of, there's a bunch of unexpected ways that physics could be different, but they'll still kind of flow down to the same space. This isn't the main focus of the talk, but I do have some thoughts about that I think that kind of requires, you need to build in a little bit more to your expectations about what the future theory looks like in order to kind of make that work in a way that's not just the same sort of realism versus instrumentalism debate over again. So here's I was saying to someone at the start that I'm really bad at drawing diagrams, but here's my diagram of what I was trying to gesture towards before. But I'll just quickly go over why I think the effective realism thing is at least needs more to it. So if you start at this, this is your effective field theory, as you flow upwards into energy scales, just invert the arrows, I reused this from something else. You've got this much wider space of possibilities that are all compatible with this. But they all still fit into the same theory space, which is defined by the fields you've started with at the low energies and the couplings and symmetries you've imposed. So unless you have some expectation about what the relationship between, so suppose, just as a simple example, that the new theory looks very much like whatever the future theory is, just has a new particle that we haven't discovered yet, just like a really heavy particle. That theory actually doesn't fit into this space. It's not until you integrate that particle out in the sort of Wilson form that you can then find a theory in this space that will empirically match the predictions of that other theory in low energy, relatively low energy domains. So there's this space, while quite broad, is still kind of limiting. Unless you have some sort of principled way of connecting the other theory space that includes the more particles, or again, it could be even broader, like it doesn't have to just be a new particle. That's a simple example. You could have a completely different, it could be like general relativity to Newtonian gravity, where you have a whole different type of ontology. Unless you have some sort of principled way of going from that theory space to this theory space in a way that's not just like, oh, well, whatever happens here is going to match those predictions, then I think this just kind of collapses into the standard sort of realism, anti-realism stuff. Because if all you're saying is like, the effective field theory at higher energies will match the predictions of the future theory, an anti-realist empiricist is going to be happy with that. I think that's kind of a constraint on theory construction in physics, that we build our theories to match the empirical phenomena. So we can talk about that more later. That's a quick run through of that. Why? I mean, I'm not super this isn't entirely relevant for the idea of thinking about explanations being different. I just think that pushing this sort of stability argument into a realism requires a little bit more than what's out there right now. Okay, so the final one that I'll talk about is the continued success of the standard model. Okay, so we talked about renormalizability being a good criterion for theory construction because as long as your energy is low relative to where the theory breaks down, those will be the dominant terms. But you might think, okay, well, we've been at this particle physics stuff. We've built, spent billions and billions of dollars building new colliders. We've continued to get to higher and higher energies. And yet it still seems like more or less the standard model as is without including non-renormalizable terms. Seems to be passing empirical tests or like, within the domain of accuracy, like the bounds of accuracy of the experiments, we're getting things that are compatible with just the renormalizable terms. So like, okay, maybe that was a good theory guide back in the 70s when they could only reach, smaller energy scales, but we're orders of magnitude higher than that now. How is this still successful? So the explanation you get here kind of also requires a new, a sort of new thing you've learned. That whatever that, so I've called it lambda nu here, whatever the scale at which new physics appears, you can, very roughly, it actually turns out to be, a huge mess of placing proper bounds, but at least in principle, the sensitivity of your measurements and their compatibility with the theoretical predictions gives you some indirect constraint on this value, assuming some things about how the couplings work, the energy scales that you're currently at versus the scale at which new physics comes in. It's a very weak constraint, but it's a constraint nonetheless. And you can say that it's kind of an extra thing you need to assume here is that, look, what we found out by finding out that the standard model keeps being well predicted is that where new physics comes in is going to be a much higher energy scale than we ever really thought. Because you'd think by now we'd start to see signs of non-renormalizable terms, but we don't. And I mean, this has some also bearing on some other issues in particle physics where we have issues with exactly kind of making this thing, this sort of argument work. We have actual relevant parameters where we should be finding out where the physics breaks down, and our expectations of those relevant parameters are just haven't borne out. This is the Higgs mass problem and the cosmological constant problem where, again, there's a bit of a puzzle there. I'll set that aside, but this basically to explain the continued success of the standard model, you just want to assume that, okay, well, whatever the new energy scales is are pretty high, and that would explain why we continue to see precisely confirmed predictions, because even though we've upped the epsilon, it's still not high enough where epsilon over lambda is actually an appreciable quantity that we could start to see effects. Cool. Okay, so to wrap up, those of you who were, I didn't tell you when to fall asleep, but if you did fall asleep, I guess that's probably a good thing that I didn't tell you to fall asleep. But if you did, you can wake up now. I'll just give some quick takeaways. So again, the sort of fun little linguistic analysis of the name renormalization group was to kind of point out that this is a much richer sort of area of both history and philosophy to talk about than is sometimes gestured towards. So again, I've mentioned some papers that cover this already, and then there's this sort of reading group that I've had to duck out of it once I came here, but there was a sort of online reading group going over like 50s and 60s quantum field theory stuff at the sort of historical origins of, among other things, the renormalization group. So this included, just shouting out some people, Mike Miller, Porter Williams, Sebastian Riva, Alex Bloom, Mikhail Stolzner, I didn't put his name on here, and some others that were working on this stuff. So if you're interested in that sort of history and origins of this stuff, hopefully they'll be coming out with some works soon. I don't mean to put pressure on people who aren't here to defend themselves, but keep an eye out for those papers if they are still working on that. I'm interested in them anyway, so I wanted to shout that out. And then quickly, the contrast, what are renormalization group explanations in particle physics? So we have this sort of overwhelming formal similarity between condensed matter systems, like bulk systems that have phase transitions and such, and in particle physics that allow for this the similar application of quite similar forms of the renormalization group transformations. But despite these similarities, there are at least some differences in how you carrier interpretation. The degree, I've tried to give a non-controversial one here, that at least like the phenomenon of universality as has been widely discussed in the philosophy literature doesn't really come up in a relevantly similar way in particle physics. But nevertheless, we still use the renormalization group to explain things. We explain the stability of our theories under counterfactual variation, the success of the effective field theory program generally. We learn about the structure of theory space, including that contains the standard model as well. So cool. Thanks. I also, before I wanted to also shout out David's quantum field theory class that kind of inspired me to think about this from a slightly different angle. So though there's no citation of any of his work here, that's kind of playing a role in the background. Just wanted to throw that out. Thanks.
We'll take a 2-minute break and then we'll have plenty of time for questions.